welcome to Alex. Alex is one of the leaders in this computational statistical gaps project that's been going on in our field for a couple of years. He's one of the fellows here this semester. So he's here to tell us about optimal spectral recovery of a planted vector subspace. Take it away, Alex.
Great. Okay. So thanks a lot. This is joint work with Mao at Georgia Tech. So here is the problem I'd like to talk about today. Recover a structured vector planted in a random d-dimensional subspace. Okay, so I give you a random subspace, except that there is one particular vector hidden in it. The subspace, imagine, has dimension d much smaller than n. So n is the ambient dimension, and we're given a d-dimensional subspace inside that. And this hidden vector in the subspace that we're trying to find has some kind of special structure that distinguishes it from all the other random-looking vectors. A primary example being sparsity. So let's imagine maybe that the vector has only row fraction of entries non-zero. And those non-zeros will just basically be plus minus ones, except normalized. So we'll use this normalization. Okay. So, the motivation for this is that it's sort of a generic task in machine learning related to various other problems, but I will not spend too much time on this. Let me instead tell you kind of a precise statistical model for this problem. So the thing we're going to observe is called y. It'll be some basis times a rotation. So what does it mean? The thing we observe is going to be an n by d matrix. And we're going to think of the columns as being the basis for the subspace we are being given. And the way we generate it is like this. We first just find some basis for our subspace. And the way we do that is take this secret planted vector v and sort of just put it there as the first column, fill the rest in with a bunch of random Gaussians. Okay, so certainly the columns of this span the subspace we're interested in. But then we multiply by a random orthogonal matrix to sort of do a change of basis. This change of basis does not change the column span, so it doesn't affect the actual subspace, but it makes it so that v is not just sitting here as the first vector in plain view. Instead, we get some sort of random looking basis for our subspace. Is that okay? A slightly harder variant turns out I could just give you some arbitrary basis for the column span of V instead of this particular sort of random looking one. It turns out to not really make a difference. That with a bunch of technical work, whenever we're able to solve this one, we can also solve the slightly harder version. And so I won't really get into the difference. Okay. So let me tell you a bit about prior work. For simplicity, I'll think about this particular scaling regime. So we kind of have two parameters. One is the sparsity of the planted vector, and the other one is the dimension of the small subspace within the ambient space. And so we can think about the parameter space as being sort of this square. And there are a bunch of prior work on this problem. So here I'm specifically restricting to the case where the planted vector is like a sparse Rademacher. So first of all, information, theoretically, it's possible everywhere in the whole square by some kind of brute force search. If you kind of try all the sparse vectors, you'll eventually find it. But I want to talk about polynomial time algorithms. And so there's a bunch of prior work on this showing that certain areas here are easy. So starting with Demonet hand, then some non-convex optimization, sum of squares, a faster spectral method. Okay, so this is what the phase diagram kind of looked like before our work, and we sort of settle the rest of it. So we show that in some sense, this blue line is kind of the real barrier between easy and hard. So we have an algorithm in this whole green region. The dotted, the striped line is sort of new. And we also have some kind of evidence based on low degree polynomials for hardness in the remaining region. Okay. And so this is probably the most technical slide of the talk, so get ready. One of the key insights, it's fairly simple, but was quite important, especially for the lower bound, was to realize that this problem I told you about can actually be reframed as a totally equivalent other problem that looks maybe quite a bit different. So just to recap, this first P1 is the problem I told you already, right? We think about these columns as being the span of spanning our subspace, and we generate it in this way. And a couple new things. I'm going to call mu just the entry-wise distribution of the planted vector. So you can imagine it's some kind of sparse thing. And we're going to imagine R is a random orthogonal matrix. Now let me tell you about the other problem, which turns out to be the same. So we're now going to really think about the rows of Y instead of the columns. And what these rows are going to be, they're basically going to be, you can think of them as IID samples from a certain distribution. And what's the certain distribution? Well, first we pick some random unit vector in D dimensions. This is going to be the same for all of our samples. And then each of our samples Yi sort of has distribution mu in that fixed direction U, but in all other directions it's kind of just Gaussian, right? So a sample Yi, if I look in direction U, project into that sort of secret direction, I see the distribution mu, whatever it may be. But anywhere else, any other direction just looks Gaussian. Or any orthogonal direction looks Gaussian. Another way to write this a bit more formally is like this, that Yi is, so Vi is the distributed like mu. So this is kind of the special part in the U direction. And then this is saying Gaussian in all other directions except for U. Okay. Any questions about these two problems? Okay, so why are they the same? I claim that these literally give you the same distribution over matrices Y. Where this mu here corresponds to the same mu here, the entry-wise distribution of V. And so, okay, why is that? Right, so I've suggestively written Vi here because it does indeed correspond to the same V. Now, the less clear part is like, what does this U correspond to? So U turns out to correspond to the first row of the random rotation. And why is that? Well, this row kind of tells you, where the secret hidden coordinate gets rotated to. And it turns out the rest of the rows don't really matter because this stuff is all just Gaussian, and so it doesn't matter how you rotate it. It's all kind of rotationally invariant anyway.
This is, in some sense, the problem that goes by the name non-Gaussian components analysis.
That's entirely possible. Okay, I'm not sure if I've heard this name, but
I think we're going to hear about it tomorrow, maybe. So maybe we can figure it out after that.
Perfect.
And this is also seems, if mu is discrete, it seems a little like this parallel pancake thing that we heard about the other day.
Yeah, it's totally very related to Aaron's talk, or maybe a few talks. If I take mu to be this parallel pancake distribution, it's exactly that as well. Good. Okay, so is anyone convinced these distributions are the same? So one way to see it is to kind of look at this picture and just imagine doing this matrix multiplication and what is each row going to look like? And the claim is that it's going to look like this. If I just kind of imagine doing the matrix multiplication, I have to add up these rows with these coefficients. And so I get Vi times U, right? That's the first part here. The rest of these are orthonormal basis for everything except the U direction, which kind of gives you this part. Okay. So let me tell you a bit about the results. So there's this very nice algorithm. So we did not invent it. It comes from Hopkins, Shramshi, Stoyer. So Sam and Salil are here in the room. So the algorithm is to take the leading eigenvector of a certain matrix. So remember the Yi's are the rows of this observed matrix. Yeah.
Sorry, just about the previous thing. So are these models equivalent to the one where you would take, where you would model the orthogonal complements by subtracting out the direction and thinking more samples, that style of thing, or like, could you do?
Are you talking like the negative Wishart type of thing where you
Or
where I give you a basis? I see. Yeah, there's some question is it should I give you a basis for the subspace or should I give you a basis for the orthogonal complement of the subspace? I'm not sure. I mean, they're equivalent for polynomial time algorithms, of course. Not clear that they're equivalent for like low degree algorithms or something, I think. Is that the question?
Yeah, or I don't know, or if just for kind of technical reasons, it might be easier.
Yeah, like here I'm imagining D being a lot smaller than N. So the orthogonal complement one gets a bit weird because I'm giving you like an almost full dimensional subspace and you're supposed to, take a very small subspace that I didn't give you. But yeah. Good, okay. So what is the algorithm? It's some kind of spectral method. So you build some weird matrix and you take its leading eigenvector and you hope that this leading eigenvector will be close to U. This is the same algorithm from HSSS, except for this extra normalization term, which is not so important. And once we have U, it turns out you can get V back in a very simple way. I won't try to explain maybe why this particular thing, but maybe it makes sense that if you think of these Y's as IID samples, that you're summing over your samples of something. And okay, the something turns out to be a particular degree 4 polynomial. So what are our main results for sort of the upper bounds? So HSSS already studied this and proved kind of this condition, and we, with some extra work, kind of improved it to this optimal condition, or condition we think is optimal. Some other technical improvements are that we have guarantees in L infinity norm instead of L2, which implies that you can actually exactly recover the vector V instead of just estimate it in 2 norm. This is probably maybe the most technical part of the proof, is this leave one out analysis, but I won't try to get into that. Another thing that's new is that we can also cover sort of this dense case where rho is actually equal to 1. This is just a plus or minus 1 vector. So a planted Rademacher vector in a subspace, similar to Aaron's talk. And so here, there's a spectral method succeeding when D is smaller than N, and we think it's hard when D is big.
This week, I think, okay, I don't exactly remember what was in our paper, but like probably it was the constant sparsity kind of regime, like a 1/10 non-zeros or something, I guess. And you're saying that like completely dense is just as easy.
Yeah, that's right. It doesn't.
With the same algorithm.
So there's kind of a twist, which is you have to look at the bottom eigenvector now instead of the top, which I'll tell you why in a second. But yeah, basically the same algorithm still works.
The intuitive, okay, I guess, yeah, go ahead, sorry.
Yeah, so here's roughly why this algorithm works at a very high level. You can start by saying, what's the expectation of this, right? This matrix we want to analyze. Turns out to be a nice rank 1 thing in the direction U, right? So that's going to help us have a top eigenvector close to U. But then there's this term, this kind of signal to noise ratio, is the 4 norm of the hidden vector minus 3n. And 3n is the 4 norm of like a random Gaussian vector. So somehow this term is measuring, how much does the 4 norm of our vector differ from that of a random vector? So if this thing is sort of big, either positive or negative, that's going to be good for us, right? It'll either give us a big positive eigenvalue or a big negative one. Then the rest, so all kinds of technical work is hidden here, but the rest is to bound sort of the spectral norm of the remaining part and say that it's not too big. And in the end, you get some condition that just looks a bit complicated, but depends on sort of the 4 norm of the vector and so on like this. And so, for example, in this sparse Rademacher case, this is the conditions for the algorithms to succeed. This is what I wrote before. But then there's also this other thing that the sparsity rho should be bounded away from 1/3. Why is this? Sparsity 1/3 happens to be the point where the 4 norm of a sparse vector exactly coincides with that of a Gaussian vector. So this algorithm would not work in that sort of that case. Yeah.
Sure. Is there some easy to see reason why the norm makes sense?
Yeah, why the 4 norm good? Well, the second norm won't tell you anything because we've normalized things to make that the case. Same as like the third norm if your thing is distribution symmetric. The fourth norm is kind of the first degree where you hope to gain something. And so that's what this algorithm is using. But there possibly if say your vector matches maybe the second and fourth moments of the Gaussian, maybe there's some higher order 6th degree spectral method that also works. I don't know what this looks like, but yeah, potentially there's some other algorithms that would exploit this. Yeah.
Well, I'm just wondering about a quiet ending where I match the first t moments of the Gaussian with my distribution and try to make it harder and harder for you to create these algorithms.
Yeah. Right. Yeah, you could certainly do that. I mean, I think we have ways to at least predict how hard it should be using this low degree stuff, which I'll get to in a second.
I think in a sense that is parallel pancakes. Yeah, the parallel pancakes hard example is in the non-Gaussian direction, making a discrete distribution which matches as many moments of Gaussian as you can.
Great, so that's it for sort of the upper bounds side. Let me talk about the lower bounds now. So if we want to convince ourselves this problem is hard, what do we do? Well, the first thing to note is that it would be sufficient to talk about hardness of a certain detection problem. So, if you want to say that it's hard to recover the planted vector, we can instead think about trying to show that it's hard to just distinguish these two things. So this is the same exact distribution from before. This is what we call planted. And then we're going to compare that to null distribution where just the whole basis is IID Gaussian with no special planted vector. Okay. And the goal is now that I give you a sample, I give you this matrix Y that comes from one of the two distributions, and you just have to tell me which one it was. And it turns out you can show that if this detection problem is indeed hard, then this implies that it's also hard to recover the vector V. Hopefully this is quite intuitive and can be formalized by a polytime reduction, but I won't get into this. And so, how are we going to argue that this problem is sort of hard? Well, remember that this was some spectral method that succeeded in the easy regime, right? What does it look like? It's some D by D matrix where each entry is a particular degree 4 polynomial in the entries of Y, right? Kind of 2 degrees coming from here and 2 from here. And so we know that in the easy regime, you can solve the distinguishing problem just by sort of thresholding the biggest eigenvalue in absolute value of this matrix. This kind of follows from the analysis before. And so we might wonder maybe there is a better spectral method, right? Why did I pick this particular polynomial? I could pick different polynomials, maybe of degree 6 or 8 or something higher. But we in some sense show that this won't help you, at least for this sparse Rademacher distribution on the vector, that actually any polynomial sized spectral method with constant degree, whose entries are constant degree polynomials, is not going to succeed in sort of this conjectured hard regime. Okay, here's a bit of a more formal statement of this if you're feeling ambitious. But essentially this is saying in the easy regime, there is some matrix where you can kind of threshold the spectral norm in order to tell these two distributions apart with very high probability. Right, spectral norm is like above twice something in one case and below just 1 times something in the other case. Whereas in the hard regime, any poly-size spectral method, and no matter what threshold you try to pick, you're not going to be able to separate the two cases even by sort of a 1 plus epsilon versus 1 ratio. The main sort of weakness in this result is right here, is that we're only ruling out spectral methods that have a fairly high probability of success. The actual thing that succeeds in the easy regime has a way better probability. But it would be ideal to improve this to say just little o of 1 or something. So I think that's a nice open problem. That's not really specific to this planted vector, but is something present in all of these types of low degree lower bounds. Okay, so together these things sort of say that this thing really is the fundamental threshold for when spectral methods can succeed. Okay, so as maybe I've alluded to, and some of you can guess, how are we going to prove spectral methods fail? It's going to be using low degree polynomials. So the two steps to show spectral methods fail. First, kind of show any spectral method can be implemented as a low degree polynomial. Specifically, if you take your matrix, raise it to a big power, and take the trace. This is kind of approximates the biggest eigenvalue. You turns out to need like logarithmic degree. This exponent needs to be like logarithmic for this to work. Whereas on the other hand, we're going to prove that any low degree polynomial in the hard regime cannot succeed at detection in the sense of this kind of low degree likelihood ratio, which has appeared this week in a few previous talks, kind of saying no low degree polynomial can have a large expectation in the one distribution while having kind of small fluctuations in the other. And like we've heard a lot this week, this kind of falls into a long line of work on low degree lower bounds, starting from many people in the room, and for all sorts of different average case statistical problems, it's kind of been shown that low degree polynomials are actually as powerful as the best known algorithms for these things. And so this framework kind of provides a unified explanation for why these things are hard. Okay, here is one last kind of technical lemma that gets a little bit into the proof. So if you remember this this sort of general setup that I talked about, where you have these IID samples that have a specific direction, specific distribution in one direction and Gaussian everywhere else. And I'll make it even a bit more general by saying that the planted direction itself can be drawn from whatever prior you like. Here's sort of the key, technical step in the proof is to actually give an equation for this advantage. So this thing I called advantage here is just how much can low degree polynomials, how well can they distinguish this ratio from before. And it turns out for this general type of problem, there is kind of this nice closed form solution for what it looks like. And it kind of decouples nicely into two parts. This one just depends on the planted direction u. So this is like two independent copies of u, and it has to do with their correlation. Whereas this is something that has to do with the planted distribution itself, mu. And these h's are Hermite polynomials. So these Hermite expectations would be 0 if your distribution mu were Gaussian. This is in some sense measuring how non-Gaussian is that planted distribution. Okay, and once one has this formula, you can sort of plug it in for any type of problem you have of this form and get lower bounds. Okay, so we're about out of time. So just to summarize, we talked about a planted sparse vector in a subspace. There is this reformulation of it into a different problem. And we improved the analysis of this existing spectral method, succeeding under some conditions, or more generally, just leveraging the difference between the forenorm of R vector and the Gaussian. And then we have sort of this matching lower bound saying no spectral method can do better, and so on. One open problem here, which I stole from Guy actually, is whether we can do reductions in present. Thanks, that's all.
Question for Alex.
Maybe I can ask something about the spectral method. Like, I'm guessing that this might have come up from some of these SOS kind of considerations. So, is there also a way to think about it from like TAP, Kikuchi, like some statistical field kind of formulation? Linearization of that?
Yeah, I don't know of any way to come up with it like that. That's a good question. Anyone have a better answer?
It does correspond to the natural sum of squares certificate, but I don't know how to think about it.
Did you start to recover the SK model for like sparsity 1 and like dimensional of the subspace going to 0, like delta n? Because it's like a Boolean vector planted in a very small dimensional subspace, in which case it's like the max eigenspace of your random GOE matrix.
Yeah.